In the last lecture, we have seen the concept of pointwise convergence and uniform convergence, and we have seen how to define topologies that relate to these types of convergences. And in this lecture, we will study the notion of equicontinuity, which is closely related to the uniform convergence of a sequence of functions. So let us give a definition for this. So we consider a subset f of the set of continuous functions from x to y, where y is a metric space. Now we have seen that when y is a metric space, we can give the subspace topology coming from the uniform topology on the set of all functions from x to y, and that is closely related to uniform convergence. Now we have the following definition for equicontinuity of this subset f. So let us choose a point x naught in X. Then the set f is said to be equicontinuous at x naught if given any epsilon greater than 0, there exists a neighborhood u of x naught such that we have for all x in u and f, a function in this subset f, we have that the distance between fx and fx naught is less than epsilon. So an immediate remark is that if f consists of a single function, so let me write it here, remark, or rather this is bunch of remarks. So the first remark is that if f is a singleton set which consists of a single function f from x to y, f continuous, then equicontinuity of f is equivalent to continuity of f. So notice that if f is continuous at x naught, so at x naught, let us remind the definition of continuity of function of the function f at x naught when y is a metric space. So this is equivalent to saying that given epsilon greater than 0, there exists a neighborhood u of x naught such that the distance between fx and fx naught is less than epsilon for all x in u. And this is basically the same definition here for equicontinuity, except that we have a bunch of functions. So now if you have a single function, then you can choose this neighborhood u to be the neighborhood u here, and the definition the two definitions are equivalent. However, if you have more than one function, then equicontinuity says that you can choose a single neighborhood u which works for all functions in this subset of functions f, and this is the main difference between continuity and equicontinuity. So equicontinuity can be seen as a generalized version of continuity of a single function. So another remark that I just mentioned is that the same, so if f is equicontinuous and x0, then the same neighborhood u of x0 works for all functions f in the subset f. So in general, if you have many different functions, you will need to choose different neighborhoods for this condition to hold for each of these functions in f. And so equicontinuity is a stronger notion which allows you to take only one neighborhood that works for all functions. And let us now define the equicontinuity of a subset of functions. So f is said to be equicontinuous. So rather than saying equicontinuous at a point, we simply say that it is equicontinuous if it is equicontinuous at all points x0 in x. So similar to the definition of continuity at a point and continuity as a function, we say that it is equicontinuous if this equicontinuity at a single point holds for all points in x. And now let me continue with the remarks. So further remarks. So the first one is that if f is a finite set, meaning that it has only finitely many functions, so f is some set of functions f1, f2, fn. This is a subset of continuous functions from x to y. Then f is equicontinuous. So to say this proof, so choose, since each fk is continuous for any x0 in x, choose neighborhoods uk of x0 such that x belongs to uk implies that the distance between fkx and fkx0 is less than epsilon. So here I'm choosing let epsilon be greater than 0, and let me rewrite this. So we start, of course, with an epsilon greater than 0, and we use the continuity of each of these functions fk to get these neighborhoods uk, and now define u to be the intersection of all these neighborhoods un. Then this is an open set containing x0, because x0 is contained in each of these uk's, so the intersection also contains x0. So u is a neighborhood of x0, and we all have that d of fkx0 is less than epsilon for all k in this set 1, 2 up to n, and this is because x belongs to each of these uk's, so the same neighborhood will work for all these functions fk. So we see that if you have a finite set, then it is equicontinuous. Of course, finite set of continuous functions, then this subset is equicontinuous at all points. Okay, so this implies that f is equicontinuous at all points x0 in X. So now the second remark is that if f1 is an equicontinuous is an equicontinuous subset of Cxy, and f2 is also equicontinuous, then the union f1 union f2 is equicontinuous. So in particular, if one of them is finite, in particular, let's say if f2 is finite, then f1 union f2 is equicontinuous, because finiteness guarantees equicontinuity. So to show this proof, so we begin with the equicontinuity of f1. So again, let us choose, let epsilon be greater than 0 and x not belong to X. Then we choose, since f1 is equicontinuous, so there exists a neighborhood u1 of x0 such that we have for all x in u1 and for all f in f1, we have that the distance between fx and f of x0 is less than epsilon, and this same neighborhood u1 works for all the functions in this equicontinuous set f1. Similarly, there exists u2 of x0, neighborhood of x0, such that for all x in u2 and for all g in f2, we have that d of gx and gx0, the distance between gx and gx0, is less than epsilon. So if take again the intersection u to be the intersection of u1 and u2, this implies that if you take any function, let's say h, in the union of f1 and f2, then we have that for all x in u, we have that d of hx and hx0 is less than epsilon. So this implies that the union is equicontinuous. So this shows that f1 union f2 is equicontinuous. So an immediate corollary is the remark that a finite union of equicontinuous sets is equicontinuous, just by induction and the previous result. And now we will describe the relationship between equicontinuity and uniform convergence of functions. And this is arguably the most important relationship in the context of equicontinuity, and it is closely related to uniform convergence. So let us see why this holds. So let us see a theorem describing this relationship. So here's the statement of the theorem. It says that sequence of functions, continuous functions, fn, converging uniformly to function f. Remember that by the uniform limit theorem, f is continuous. Then the set of functions, the set of the sequences, the functions making up the sequence, which is a subset now of cxy. This is an equicontinuous set. So let us show this. So let epsilon be greater than 0, and we choose a point x0 in x, and we will show that there exists a capital N such that the set f capital N, which is just the terms in the sequence which are greater than or equal to, which have index greater than or equal to n, this is equicontinuous. And this would imply that f, which is the union of the set finite set f1, f2 up to f capital N minus 1, union fn is equicontinuous by the second property above. So it suffices to show that this f capital N is equicontinuous for some, there exists some capital N for which this is equicontinuous. So we have to show that there exists a neighborhood a u of x0 such that for all n greater than or equal to capital N, we have and for all x belonging to u, we have that the distance between fnx and fn x0 is less than epsilon. So to find this capital N, let us note that the distance between fnx and fn x0 is by the triangle inequality bounded above by d of fnx fx plus d of fx fx0 plus d of fx fx0 fn x0. And so this is, note that this holds for all n in n. And now choose capital N in n such that we have d of fnx fx is less than epsilon by 3 for all n greater than or equal to n and for all x in x. This is possible since fn converges uniformly to this function f. So possible by uniform convergence of fn. And now this implies that okay, so let us keep this in mind, and now we can choose by the uniform limit theorem, which we saw earlier. F is a continuous function. So this implies that there exists a neighborhood, a u of x0 such that for all x in u, we have that the distance between fx and fx0 is less than epsilon by 3. And therefore, this implies that also for all x in u and for all n greater than or equal to capital N, we have the following, that d of fn x fx is less than epsilon by 3, d of fn x naught fx naught is less than epsilon by 3, and d of fx naught is also less than epsilon by 3. So if you sum this up and use this triangle inequality here, so let me call this star, and then each of these terms is less than epsilon by 3, this is also less than epsilon by 3, and this is also less than epsilon by 3 for all these x in u and n greater than or equal to capital N. So we are using these three inequalities, and now this implies that for all x in u and for all n greater than or equal to capital N, we have that d of fnx naught is less than epsilon, and this is by the inequality star above. So we have shown that the set f capital N is equicontinuous because the same neighborhood works for all of the functions in this set, and this concludes the proof. F is equicontinuous. Now let me end with a couple of final remarks. First is that the equicontinuity, the definition of equicontinuity does not depend on the topology of CXY, because it only depends on the metric that we used on Y. Otherwise, it does not mention anything about the topology of CXY. Also, it only depends on the metric D on Y and not on the topology on Y, which means that even if you have two different metrics that give you the same topology, then a set of functions can be equicontinuous for one metric but not equicontinuous for the other metric. Also, it depends on the chosen metric D on Y, and rather than just the topology on Y. So note that we have the specific metric coming in the definition, and so it depends, the concept of equicontinuity depends on this metric. And the last remark is that equicontinuity is closely related to the compactness of the closure of F in the uniform topology. And this is illustrated by the Arcela-Ascoli theorem, which we will see next week. So it holds a very important place, especially in mathematical analysis, because you are always trying to consider a set of functions and whether that set is compact under some topologies on the continuous functions from x to y. So this ends our brief discussion of equicontinuity just from the definitions, and in the next lecture we will see the close relationship of equicontinuity with the concept of totally boundedness.